So to continue, we have two examples left. So for our second to the last example, let's take a look at the following. A curved lamina in the shape of the cylinder z equals square root of 4 minus x squared above the rectangular region on the xy plane bounded by the lines x equals 0, x equals square root of 3, y equals 0, and y equals 1 has density function delta equal to x plus y. We're asked now to find the mass of the lamina. So recall that the mass m is equal to the surface integral over the surface S of the density function. So that would be x plus y d sigma. So what's left for our case is to determine which is our surface S for this case. So again, the surface S actually gives you the shape of the lamina or the shape of the surface. So that would be, for this case, S would be z equal to the square root of 4 minus x squared. The region on the xy plane is actually bounded here by four lines: x equals 0, x equals square root of 3, y equals 0, and y equals 1. So there's actually no need for us to sketch here the surface, since all we need to know is um, what is the region on the xy plane. But again, the region R is actually a simple rectangle. So that is, if these are the x and y axis respectively, x is from 0 going now to square root of 3, while y here is from 0 until 1. And so we have here this rectangular region, which is our region of integration. So since z is equal now to square root of 4 minus x squared, we could take a look here at z, or at the surface, as something which is Cartesian defined. So the square root of 4 minus x squared is denoted by g of xy. And so for our solution, this is equal now to the double integral over the region R of x plus y. We want to express here, since we're projecting onto the xy plane, everything in terms of x and y. So the density function is retained. D sigma is replaced by the square root of 1 plus g sub x quantity squared. You could compute here that the partial derivative of g of xy with respect to x is actually negative x divided by the square root of 4 minus x squared. While g sub y, since y is no longer present in this term, then the partial derivative with respect to y is 0 dA. And so to simplify, we have here the double integral over the region R of x plus y. Simplifying here the term inside the square root, we have here the square root of 1 plus x squared divided by 4 minus x squared dA, or that is, we want to compute the double integral over the region R of x plus y. The numerator now, using an LCD of 4 minus x squared, would be 4 minus x squared plus x squared. So that would be the square root of 4 for the numerator divided by 4 minus x squared for the denominator dA. And so we want to compute now for the double integral over R of 2 times x plus y divided by the square root of 4 minus x squared dA. So to continue, the mass m now is equal to the double integral over R of 2x divided by the square root of 4 minus x squared dA plus the double integral over R of 2y divided by the square root of 4 minus x squared dA, where R here is a rectangular region. So you could integrate first with respect to x or with respect to y. It doesn't matter, in fact, since the region is rectangular. So I'll use the order dy dx. So this would now be equal to the integral. X is from 0 to square root of 3. Y is from 0 going to 1 of 2x divided by the square root of 4 minus x squared dy dx, plus, similarly, you have here 0 to square root of 3, 0 to 1, 2y divided by the square root of 4 minus x squared dy dx. So integrating both with respect to y, notice that this is constant with respect to y, so its antiderivative is that term times y. So you have here the integral from 0 going to square root of 3 of 2xy divided by the square root of 4 minus x squared, evaluated from y equals 0 going to y equals 1 dx, plus you have the integral from 0 to square root of 3 of, for this case, the denominator is constant with respect to y, so we're multiplying here the denominator with the antiderivative of 2y. So that would be y squared divided by the square root of 4 minus x squared, evaluated from y equals 0 going to y equals 1 dx. And so this is equal now to the integral from 0 to square root of 3. When y is 1, you have here 2x divided by the square root of 4 minus x squared dx, plus the integral from 0 to square root of 3 of, when y is 1, we have here 1 divided by square root of 4 minus x squared. When y is 0, the numerator is 0. And so we're left now with integrating here these two terms. So for the antiderivative, notice here that we'll basically use a simple substitution of 4 minus x squared since its derivative is negative 2x dx. So what we have here would be something of the form negative u raised to minus 1 half. So you could compute by yourselves that the antiderivative of 2x over the square root of 4 minus x squared is actually negative 2 square root of 4 minus x squared, evaluated from 0 to square root of 3, plus, for the antiderivative of 1 over the square root of 4 minus x squared, if you recall the formula, this is equal to the arc sine of x over 2, evaluated from 0 to square root of 3. And so, this is equal now to, when x is equal to 3, you get here inside square root of 4 minus 3, which is square root of 1, which is 1, so this is negative 2, minus, when x is 0, 4 minus x squared is 4, the square root of which is 2 times negative 2, so that would be minus 4, plus, for sine inverse of x over 2, when x is square root of 3, we get here pi over 3. When x is 0, you get 0. Or, this is equal now to negative 2 plus 4, which is 2, and then plus pi over 3. And so this is our answer for item number 1, part number 2 for the mass. If you have questions, feel free to pause and rewind the video or comment down below. We'll proceed with example number 2. Here, using a surface integral, you're asked to find the surface area of the part of the cylinder x squared plus y squared equals r squared, where r equals 0, in between the plane z equals 0 and z equals h. So, actually, without using a surface integral, we should know the answer for this case. So to sketch, we have here a general cylinder x squared plus y squared equals r squared. So say I'll name this r and minus r respectively, and then say that this is h. And so constructing our circle, x squared plus y squared equals r squared on the xy plane. For example, you have here the following. And then extending that onto the direction of the positive z-axis, since we want here the cylinder in between z equals 0 and z equals h. What we have here would be the following. And we're taking a look now at the surface area of this portion in front, as well as that of the back. So again, we know that the height for this case is h, and then the radius of the base is actually r. And so since we only want here the lateral portion of the cylinder not including the top and the bottom, of course. Then the surface area is in fact given here by 2 pi rh. So using a surface integral, we aim to actually obtain here the same answer. So we could do this in two things. Um, One is to take a look here at x squared plus y squared equals r squared, which is our concern, as something in terms of a parametrization, or we could take a look at it as is. So that is in terms of a Cartesian equation. So for our solution, let's take a look here at our alternatives. So for our first option, since we're concerned here with the cylinder x squared plus y squared equals r squared, we could take a look here at a parametrization for x squared plus y squared equals r squared. So you could recall actually the concept of cylindrical coordinates, in which case here, the surface S is given now by r of uv. Using cylindrical coordinates, its first component is r cosine theta, so you could use here uh, v cosine u, again v cosine u, where v for this case is actually the radius, so that would be r cosine u. V sine u for the y coordinate, so that would be r sine u. And then the last one would be the z coordinate. Notice here that the z coordinate is varying from 0 going now to h, so we could use that as another parameter. Or for this case, u is in between 0 to 2 pi for us to generate the whole circle, and for us to actually get the height at each point, then v here should be from 0 until h. So in which case now, since we have a parametric surface and we're taking a look at the surface area, we're setting here the density function to 1. So we're taking here the surface integral over S of 1 multiplied now by d sigma. So it remains for us to actually determine the norm of RU cross RV. So from the given parametrization, take note here that RU is actually negative R sine U, R cosine U, and then 0, while R sub V is actually equal to 0, 0, and then 1. And so the cross product of RU and RV is now equal to R cosine U minus 0 is R cosine U. Negative R sine U times 1 minus 0 is negative R sine U. Middle component is negated further, so that would be R sine U. And then you have here 0 minus 0. So this is 0, in which case the norm of RU cross RV is actually equal now to the square root of R squared cosine squared U. This is R cosine U quantity squared plus R squared sine squared U, just R sine U quantity squared. And factoring here R squared, you're left inside with R squared times the quantity cosine squared plus sine squared, which is 1. So we're taking the square root of R squared, which is R since R is positive. And so the surface area now is equal to a double integral over the region R on the UV plane of 1 times the norm of RU cross RV is R, and then you have here dA, so that would be du dv or dv du. But recall here that u varies from 0 to 2 pi, so these are constant boundaries. Same goes with 0 and same goes with v, which is from 0 going to pi. So you could use dv du or du dv. So I'll use here dv du. Oops, I might have made a mistake here. V here is the z coordinate. but the v for this, or the z coordinate here, varies from 0, xy plane, going now to h. So um, I'm replacing this by h. Again, dv, v is from 0 to h, du, u is from 0 until 2 pi. And so integrating here r with respect to v, we have here the integral from 0 to 2 pi with respect to u of rv, where v is evaluated from 0 going to h du, or this is equal to the integral from 0 to 2 pi. When v is h, you have here rh. When v is 0, you have here 0. So we integrate rh with respect to u. RH is constant with respect to u. Its antiderivative is RHU, where u here is from 0 until 2 pi. And so, when u is equal now to 2 pi, we have here 2 pi RH. When u is equal now to 0, you get 0. And so, you obtain here this answer, 2 pi RH, which is expected for this example. If you have questions, especially when it comes to how this parametrization is obtained, you could depend on the cylindrical coordinate system. Once again, the cylindrical coordinate system turns the circles in polar going now to cylinders in the cylindrical coordinate system. So you could take a look at another option of looking at x squared plus y squared equal to r squared as a Cartesian defined surface. However, take note here that the only way for us to define x squared plus y squared equals r squared in terms of Cartesian would be to write here either x equal now to a function in terms of y and z, or y equal now to a function of x and z. There's no need for us to introduce z, since z is actually a free variable for this case. It varies from 0 going now to h. So let's use here this portion. So notice that if we use something of the form x equal to g of yz, then we want to project onto, again, we're replacing x by something in terms of y and z. So we want the projection onto the yz plane. But notice, if we want here to write x in terms of y and z, this in fact poses a problem, because once we attempt to write x equal to g of yz, then x squared plus y squared equal to r squared would imply here that x is either a positive or a negative square root of r squared minus y squared, but we only need one in fact. So what we could do is to actually restrict the graph of the whole cylinder into something in terms of its parts. So for example, you could take a look here at the portion of the cylinder in the first octant, since the surface area there should be equal to the surface area of the one at its back, and then at each of the left-hand parts. So you could take a look at 1/4 of the whole surface. So if instead we consider, for this case, the cylinder x squared plus y squared equal to r squared in the first octant. So that is, for this example, say this is r for x and y respectively, and then we're extending until h along the z-axis. So what we have here would be would be this portion, and then we're projecting onto the YZ plane. So for the projection R onto the YZ plane, notice that what we have in fact is this portion as its projection onto the YZ plane, which is in fact a rectangular region. So the rectangular region for this case is bounded by 0 and R for Y and 0 and H. Again, 0 and R for Y. And then we're using 0 and H for Z. So say if this is Y and then this is Z, Y is from 0 to R, Z is from 0 to H. So we have here this portion for our projection. And so S now, since we're restricted in the first octant, X and Y are positive, X now can be written as the square root of R squared minus Y squared. And so the surface area equal now to the surface integral over S of 1 times d sigma can be written now as a double integral over the region R on the YZ plane of 1 multiplied by the square root of 1 plus g sub y squared plus g sub z squared, where here the square root of r squared minus y squared in fact serves as g of yz. And so this now is equal to the double integral over the region R of 1 multiplied now by the square root of 1 plus g sub y squared would be g sub y in particular is 1 over 2 square root of r squared minus y squared times negative 2y plus g sub z squared is actually 0. And so this is equal now to the double integral over the region R of the square root of 1 plus you have here r squared minus y squared for the denominator. The numerator here is y squared. Once you simplify, dA, or we're taking here the double integral over the region R of R divided by the square root of r squared minus y squared dA, in which case this is equal now to, in terms of y and z now, z, take note, is from 0 going to h, y for this case is from 0 going now to r, and we're taking here the integral of r divided by the square root of r squared minus y squared, first with respect to y and then with respect to z. With respect to y, notice we could use here the sine inverse function. So we have the integral from 0 to h with respect now to z of r times sine inverse of y over r, evaluated from y equals 0 going to y equals r dz. And so this is equal now to, when y is r, you have here sine inverse of 1, which is pi over 2. So you have here the integral from 0 to h of pi r over 2 minus, when y is 0, sine inverse ng 0 is 0. So you have here pi r over 2. Integrating this with respect to z, this is constant, take note. So you have here pi r z over 2 evaluated from 0 going to h. And so this is equal now to pi r h over 2. But take note here, we're only taking a look at the surface area of 1/4 of the whole cylinder. So this is actually SA over 4. And so the surface area would now be 4 times pi RH over 2, or this is equal now to 2 pi RH, which is, again, what we obtained in our first solution. And so this ends our examples for this discussion. If you have any question, feel free to comment down below or ask your discussion teachers. If you need any practice, you could take a look here at the following exercises. We'll be uploading answer keys of these exercises in Novelet. You could ask your discussion teachers for help. Um, if if you're aiming to answer these exercises, please do answer them first before searching for the answer key in Novelet. That's all. Thank you. Have a good day.